Okay, so good morning, everybody. This is the first session concerning the course Malliavin calculus and Monte Carlo methods. And let's say during the two first sessions, we are not going to speak about Malliavin calculus, but I want to introduce what will be our technical problem in this course, and I will start to do this today. So the idea for the two first sessions will be to do some reminder concerning Monte Carlo methods. What are they? Okay, and to see in the very basic framework of the Black and Scholl model what may be the numerical challenges that can appear, okay, in this situation, and why, okay, some tools related to the Malliavin calculus will help us, okay, to overcome these drawbacks. Okay, so let's start with my screen. So you have here the bibliography of the course. So as usual, okay, you will be able to find on my website, okay, here, all the documents that are related to this course. So I will post on this website, okay, the videos each week with the corresponding slides. You won't have lectures notes for this course, okay, but you will have precise slides, okay, that I will comment during the session. Okay, so here you have some courses, okay, about probability theory, a course of stochastic calculus, okay, so the one that I do in IRFA diploma, okay. So I believe that my course will be, let's say, self-contained, okay, but you have these references if you need more precisions, okay. So typically here you have the Black and Scholl model that is done, okay, in these two references, okay. Here it's more probability theory. Okay, so the study plan will be the following. So today, I think that mainly I will present, okay, a little introduction concerning Monte Carlo methods, okay. So I won't spend too much time on this topic because this topic could be a course apart, okay. But I just want to remind you, okay, the basics of this approach in order to approximate expectations. If you want more details on the topic of Monte Carlo methods, okay, you have on my website, okay, so you have here the teaching part of my website, okay, that you start to know. You will have here the part concerning Malliavin calculus, okay, where I will post my video. And in my previous teaching, okay, you have a part below here concerning the introduction of Monte Carlo method in finance, okay, and you have slides here that can help you. So I don't remind if they are in French or in English, but you have this one in French maybe and this one in English, okay, and they are mostly the same, okay. So if you want to have more precision on Monte Carlo methods, okay, you have these documents that are available, but that are not mandatory in order to follow this course, okay. So it will be an introduction, and then, okay, in the very basic framework of the Black and Scholl model, the idea will be to show you on little example how to use in practice Monte Carlo methods and what are the problems that can arise in this situation, even in the very simple framework of the Black and Scholl model, okay? And it will be the way to introduce why we need some tools in particular to compute the Greeks, okay, using these Monte Carlo methods, okay. So it will be the the study plan of the, let's say, the two first session, more or less, okay, before to start the more mathematical part of the course relative to Malliavin calculus. Okay, so presentation of the problem. Okay, so when we want to use Monte Carlo method, okay, what we want to do, in fact, we want to approximate integrals that may be written this way, where you have mu here that is a measure, okay, and that you are not able to compute explicitly, okay. In some sense, you don't have a primitive for f, okay, or not an easy way to compute it. And when we deal with Monte Carlo methods, we are looking for a stochastic algorithm. So by stochastic, I mean that something that is in the framework of the course of probability, let's say. And I want to have what? Okay, I want to have an estimator of this integral, an approximation, let's say. I want to be able to estimate what is the error I do when I use this approximation to approximate this integral. Okay, and of course, at the end, if possible, I want to have a good accuracy for this methodology and a computational cost that is not too huge. Okay. So before to present this thing, okay, let me remind you, okay, some approach in order to approximate an integral in the case of classical analysis. So just to tell you that approximate an integral, okay, is a problem that occurs, okay, very frequently in a wide field of areas, okay, and typically in this course, I will be interested in the framework of mathematical finance, because you know that in the case of mathematical finance, a price is given by an expectation or a conditional expectation. Okay, sometimes it's not possible to compute them explicitly, so I want to approximate. And what is more, okay, you have two important problems in finance that are to price and to hedge. And if I want to hedge, you know, for example, in the case of the Black-Scholes model, that in order to find the composition of the hedging portfolio in the Black-Scholes model, I need to compute what we call the delta that is none other than the derivative of the price with respect to the underlying asset, okay? And so I have the derivative of a price to approximate, that is the derivative of an expectation. And so I have to approximate both the derivative and the expectation, okay? And it will be exactly the question I want to answer in this course, okay? But you have other application in biology and also, okay, the historical application that was, okay, to allow the computation of quantities related to the Manhattan Project, okay? So before to show you an historical example concerning Monte Carlo methods, okay, let me remind you few things concerning approximation of integrals, okay, by tools from classical analysis. So we are here in the framework of classical analysis. That is to approximate my integral without using the course of probability. Okay, so we are going to be in the following very basic situation. So I consider a mapping F. Let's consider it from 0, 1 into R. And I suppose it to be continuous. Okay, C0 means continuous. So I can do a picture here. Okay, so I suppose that I will take it positive, okay? And I suppose that my mapping is equal, why not, to something like this, okay? So you have 0 here and 1, okay? So what I know in this case, because I have a mapping that is positive, is that, okay, the part in black here, the part in black represent the integral between 0 and 1 of f of x dx. Okay? So it's something that I want to approximate. In order to approximate, okay, we are going to use first a discretization of the interval 0, 1. So we are going to consider a regular discretization here, let's say of step size 1 over n. So a discretization this way. And what we are going to do here is in fact to approximate. So if I am between k over n and k plus 1 over n, we are going to approximate this area here, that is just the integral between k over n and k plus 1 over n, by the area of this rectangle here. So here in a red, what I have the area of this rectangle, and here the rectangle is built this way. Okay, here you have f of k over n, that is the value, okay, of the second coordinate of this point here. And so what I have in red here is simply by the area of this rectangle, this length is equal to fk over n, and this one is equal to 1 over n. So in red here you have fk over n divided by n. And in fact, the approximation we are going to use here is to say that I will approximate the integral between k over n and k plus 1 over n of f of x dx. I will approximate it by this area in red, that is by f over n divided by n. And of course, using the Schall relation, okay, I can separate this integral as the sum of integrals over this kind of intervals. And doing the sum from 0 to n minus 1 of these integrals, I will recover this integral to obtain an approximation for the integral between 0 and 1 of f of x dx. That is what? That is the sum from k equal to 0 to n minus 1 of f k over n divided by n that I can remove from the sum. Okay, and I will give a name to this one, that will be denoted by Sn of f. And Sn of f is just by what we call the Riemann sum, as you know. Okay, so this is a Riemann sum. Okay. So what can I say about this approximation? Well, we have the following result, that is the Riemann sum theorem. That tell me that if f is continuous, so in fact I can relax a little this hypothesis. Okay, I can only suppose that f is Riemann integrable, but whatever. If f is continuous, but I have the nice property that my approximation, Sn of f, will converge when n goes to plus infinity, but toward the integral I want to approximate. Okay, so here it's the classical way to approximate an integral by the corresponding Riemann sum. Okay, and from the Riemann sum theorem, I know that, okay, this approximation will converge when n goes to plus infinity. That is when the step size here goes to 0. It means that I increase the number of points, okay, in my subdivision to obtain this. Okay. So now we are going to be interested in the error we do when we use this approximation, okay, for this integral. Okay, so the associated error here. Okay, so we are going to consider, in fact, the primitive of small f okay, we are going to consider the primitive of small f, and we are going to suppose here, if I want to control the error I do, I need to do an extra hypothesis on f, that is f is not only continuous, the condition that is sufficient in order to ensure this convergence, but I will suppose it to be C1. In the case where f is C1, but since capital F is the primitive, it implies that capital F is of class C2. And in this way, it's possible for me to apply, since F is of class C2, okay, I can use the Taylor formula at the order 2. And if I do this, so let's write the Taylor formula at the order 2 for capital F between the points k plus 1 over n and k over n. And I will obtain f k plus 1 over n that is equal to f of k over n plus the derivative of capital F at the point k over n, the derivative of capital F being small f, multiplied by the difference between these 2 points, plus the square of the difference between these 2 points, that is 1 over n squared, multiplied by the second derivative of capital F, that is just the first derivative of small f, at a point that I will denote by C n k, and where this point belongs to the open interval k over n, k plus 1 over n. Okay, so it's the exact Taylor formula at the order 2. So what I obtain with this kind of relation. So of course I have all these relations from k equal to 0 to n minus 1. And if I do the sum of all these relations, because here what you have here you have the integral between 0 and k plus 1 over n. Here you have the integral between 0 and k over n. If you do the difference of these two terms, you obtain exactly this integral here. So using this relation, I obtain that the integral between k over n and k plus 1 over n of f of x dx is equal to what? It's equal to simply f k over n multiplied by 1 over n plus 1 over n squared f prime of c n k. And so if I do the sum of all these terms, okay, I obtain that the integral between 0 and 1 of f of x dx is equal to what? The sum of this term from 0 to n minus 1 and I remark that this term is none other than my Riemann sum plus 1 over n squared and the sum from k equal to 0 to n minus 1 of f prime c n k. Okay, so I have a way to express the error that I am interested in, that is the difference between my true value and the approximated one, and I obtain this one here. Okay, so let's continue with this. So using what I have done previously, that is to write this one, okay, I obtain that the integral between 0 and 1 of f of x dx minus my approximation can be bounded by the absolute value of 1 over n square sum from k equal to 1 to n minus 1 f prime of c and k. This quantity that may be, so keep in mind that I have supposed small f to be of class C1, meaning that f prime is continuous on the compact interval 0, 1. And so, okay, f prime is bounded on this interval. So I can write this as what? 1 over n squared multiplied by the number of terms in the sum, that is n, okay? So it's a 0 here. 0, and multiply by the infinite norm of f prime. So I can write it this way. F prime infinity over n, where this one, okay, is just the supremum of the absolute value of f prime on the interval 0, 1. So here I have my error. Okay, and I see two things. I recover that this error converges toward 0 when n goes to plus infinity. So you have here a proof of the Riemann-Sum theorem in the case where f is a little bit more regular than to be continuous. But I have also the fact that my error is controlled by the infinite norm of the derivative over n. Okay? So I have a way to approximate this way. What can I say about this approximation? The first thing that I can say is that, okay, I can control my error if f is regular. It's the first thing I can say, okay? I need f to be at least C1 if I want to obtain this inequality here, okay? So typically, if f is not of class C1, but I can't apply what I have done previously, and so I can't control this way my error. Second remark, suppose that, okay, my mapping is not from 0, 1 into R, but from 0, 1 to the power D into R. So suppose that you increase the dimension of the problem. If you take f from 0, 1 to the power D into R, okay? In fact, you will obtain, doing exactly the same thing that I have done previously, that the integral that is just now a multiple integral, okay, with respect to the Lebesgue measure, minus your approximation, will be less than a constant k, okay, over n to the power 1 over the dimension of my problem. It means that if I increase the dimension of my problem, in fact, the control on my error is worst and worst. For d equal to 1, I recover this one, but for d equal to 2, I have only the square root of n here and no more n. For d equal to 3, okay, the cubic root of n, and okay, so this methodology depends on the dimension of my problem. with the deterioration of the control of the error if I increase the number of my variables, okay, in the problem. Okay, but you have here exactly the 2 points that I want to overcome when I use Monte Carlo methods. With Monte Carlo methods, okay, we are going to look for, okay, a stochastic algorithm that is a probabilistic way to approximate this integral here, okay, using sequences of random variable, where it will be possible for me to control the error even if f is not that regular, because typically, okay, in the problem we are going to be interested in, that is to price options in basic financial models, okay, we won't have this regularity. And what is more, we want a stochastic algorithm that give me an error that doesn't depend too much on the dimension of my problem. Okay, so in some sense, you see that Monte Carlo methods will appear in order to overcome drawbacks of classical analysis methodology. So the one that I have presented here is very basic. It's just the approximation of the integral by Riemann sum, okay, using rectangles. I can improve the way to approximate here to be more and more sophisticated, okay, but in fact, at the end, even if I can present in the framework of classical analysis methods that are better than this one, I will have these two problems that will appear, dependence on the regularity and the fact that I depends on the dimension. I have a dimension puzzle in this situation. And it's what I want to overcome with Monte Carlo methods, okay? And it's what we are going to see now. Okay. So let's present, okay, a classical historical presentation of Monte Carlo method, and after I will show you what are the modern foundations of this approach. So we are going to consider the following easy situation, okay? So this situation is called, okay, the Buffon needle example. Okay, so suppose that you consider, okay, I will write the slide this way here. So suppose that you have an infinite floor, okay, a very, very big floor, okay, in a very big room, okay, with equally spaced line, okay, and the distance between two lines is delta. Okay, so I suppose that I am in this situation. So suppose that my room is given by this one that I suppose to be big, okay, very big, infinite even. Okay, so I have my floor this way, and so on, and so on this way. Okay. So suppose that you drop on this floor a needle of length small l. So a needle in French is une aiguille. Okay, a needle. So I have a distance delta between two lines here. And suppose that you drop a needle here. Okay, so you drop a needle on the floor. So I have something like this. Okay, with a length small l here. Okay. And my hypothesis is that L is strictly less than delta, strictly greater than 0. Okay, I have this. The question I ask is, what is the probability that a needle that is dropped randomly intersects one of the lines of the floor? Okay, so I want the probability of intersection of the needle with respect to lines. Okay, so I am interested in the probability of intersection. So probability of intersection. Okay, I consider here this angle that is theta 0, okay? And we are going to compute the probability of the intersection in the case where theta 0 is supposed to be fixed, okay? This angle is supposed to be fixed. So I will give in a name to the extremity of the length. I will have AB, okay? So what happened when theta 0 is fixed? Okay, so when theta 0 is fixed and known, okay, I know that this length here is equal to what? So according to the property, so I have a rectangle triangle here, okay, and by Pythagoras or by the classical relationship in triangle, okay, I have that this length here is just equal to L sinus theta 0. So it's exactly what is written here. Okay, so this length here is L sinus theta 0, and this length is fixed. Okay, so since my flow is infinite, the problem of the intersection in this situation can be reduced to the problem of the intersection of this line with the needle, because you have a symmetry in the problem. You are always in this situation, okay? So if my needle is here, okay, my problem will be just how to intersect this line. What is the probability? And since I have something that is infinite with a needle that is drawn, okay, I can focus myself only on the intersection of the needle and this line that I call delta, okay? So it means that I can simply be interested in the intersection of my needle with respect to this line here because I have a symmetry in my problem, okay? So what can I say? I said that the needle intersects delta if what? But if the distance between the point A and the line delta is less than what? Okay, so is less than what? So if the distance, okay, between the point A and delta is less than L sinus theta 0. So what I say something that is wrong. So I want to have the intersection that is, okay, so it's more than B here, excuse me. So the distance between B here and delta has to be less than this length here. Okay, so if B has a distance that is less than L sinus theta 0 of delta, I am sure that the needle will intersect this line, okay? So the needle intersect delta if the distance between, let's write it correctly here, the distance between B and delta is less than sinus theta 0, okay? And so what is the probability of intersection? Well, I can do a picture like this. So I am interested in the intersection with respect to this line, meaning that, okay, I suppose that by the symmetry of my problem, okay, I can only focus on this situation with the intersection with respect to delta. Okay, so if I do a picture of this line here, what happened? I have B on this line, and I know that, okay, I need to have a distance between D and this point that is less than L sinus theta 0 if I want to intersect. So it means that I have an area that I write in green here, okay, that is okay for the intersection, where here you have the points L sinus theta 0. And here, okay, because I want to compute a probability, I remind that this length here is equal to delta. And so my probability of intersection, as usual, is what? Okay, so here I am in the continuous case, but it's the place where my intersection occurs. That will be for all the situation where the point B is less than L sinus theta 0 with respect to this point. That is here L sinus theta 0 over by the set or the length of this interval representing all the possible situation, that is delta. Okay, so my probability to intersect in the case where P0 is fixed is given by L sinus theta 0, that is this distance here, okay, the length of this interval, or this line, over the distance between two lines. Because, okay, I am in this situation, I want to obtain the probability that B lies in the green, okay, that is just the length of the green over the total length, that is delta. Okay, so this is true for a fixed theta 0. Okay, what happened when theta 0 is not supposed to be fixed? So knowing that I drop, okay, my needle randomly, it means that theta 0, okay, take uniform values. So in which interval? So just be careful, because look at me with the pen. If you have here a situation where I drop my needle this way and that I obtain something like this situation is completely equivalent to this one. So if I turn it, okay, so in other words, if you have AB here or BA, but you can't see nothing different between these two. Okay, so in fact, my remark here implies that theta 0 is uniform on, so not 0 to pi as an angle can be, but uniform on 0 pi, let's say, so contain or not, whatever. Okay, so the probability I am interested in will be what? Okay, so you have here the probability for a single theta 0 being uniform on the interval 0 pi. If I want, so the probability of intersection for, let's say here, theta 0 fixed. If I want the probability that interests me, the probability of intersection, but I have to integrate this probability with respect to the uniform, okay, measure on 0 pi. That is to compute, in fact,
this integral. I have just to compute this integral. This integral that is very easy to compute because I have a primitive for the sinus, okay, that is minus cosinus. And so here you have exactly what I have done here. And if I compute this integral, I obtain this quantity. That is my probability of intersection when I drop randomly my needle here is 2 times L, where L is the length of the needle, over pi over delta. Okay? Over delta. Okay, so suppose now that you just drop now, okay, not a single needle, but that you drop capital N needles, okay, independently. You drop them on the floor, okay, and you denote by capital X the number of them that cross, okay, a line. Okay, so you have the previous situation here. You have your infinite floor, and you don't have a single needle, but several ones, okay, and you denote by capital N the number of needles you drop, and by capital X the number that crosses a line. Okay, and I say the following: my probability of intersection here, if capital N is big, okay, may be approximated by the frequency of intersection. The frequency of intersection, that is, okay, so if I drop capital N needles, denoting by capital X the number that cross, okay, then the probability of intersection may be approximated by X over N. And from this computation, it means that X over N is more or less equal to my probability of intersection. And why this formula is interesting? Because I can transform it a little in order to obtain that pi is approximated by what? By 2ln over delta x. And you have, with this methodology, okay, from an empirical experiment that is to drop needles on the floor, you have, if you control the parameters of the problem, you have a way in order to approximate the number pi. Okay? You have a way to approximate the number pi. If I give you the distance between two lines, if I give you the length of the needle, and if I give you the number of needles that you have to drop, you can compute capital X empirically. And if you do this ratio, you will have an approximation of pi. Okay? And in fact, in 1812, okay, the French mathematician Laplace suggested to use this experiment to approximate pi this way, okay? So you have a famous practical use of this experiment that was done by Lazzarini in the beginning of the 19th century, okay? That do this experiment, okay, with L, so a length for the needle that is 2.5 centimeter, delta that was 3, okay, and capital N that is this number. And so this way he obtained, okay, this approximation of pi, okay, why not? So of course, what you can say, I can say two things here. I can say that but the accuracy is not that good, but because I know that pi is more or less 2.14 and so on, okay? And of course, it's also something that is time consuming because I have to drop all these needles to count the number that cross, okay, and so on. But in fact, it's not that bad, this approximation, because we can see that this approximation, okay, is not very far from the best that you can obtain if you want to approximate pi by ratio made of 3 digits numbers. Okay, so if you allow 3 digits here and 3 digits here, the approximation you obtain for pi here, that is this one, is not very far from the optimal one. It's not a good one, but if I want to increase, I need to allow more numbers here, more, or to increase the number of digits in my numerator and my denominator. Okay. So the advantage of this technique is that, okay, with modern tools, okay, I can't generate needles using a computer. I can generate a floor using a computer, and so I can do this, okay, very quickly, okay, to approximate my pi. So you have here an example of such a situation where, okay, you can drop needles this way. So you have the link here where you are going to be able to do this. So I can just have a look if it works. Okay, so just let me 1 second, okay, to see if I can use it. So excuse me, I just want to see if it's possible to have it live. Okay, it works again. To do it with you. Okay. So I have this one. So I have to recover my doc. Okay. So is it working again? Let's see. So screen, here it works. Okay, so you have here, okay, the explanation. So okay, I can drop. Okay, so you have here my infinite floor. Okay, and in fact you do the restriction in the algorithm in order to be sure that you will be okay between these two lines. Okay, so I drop 100 for 1000, and we are in this situation here. Okay, we are in this situation, and you see that using more or less the same argument than the one that I have used previously, okay, in the computation of the needles, okay, then what I obtain an approximation that is 3.19, okay, something that is good, let's say, okay, and I can, what is nice is that I can increase the number, and that it is okay. It's a little bit too much here, let's say 10,000. You see that it's really quick, okay, to do this, okay, and I obtain here something that is more and more precise, okay. So the experiment of Lazzarini can now be done, okay, using very easily, okay, computer programming, and then to see if I intersect or not the lines. And because, okay, what is a needle from a computational point of view? A needle from a computational point of view is just to choose randomly one point and to choose another point randomly with a distance, okay, that is exactly the length of the needle. Okay, so 2 points randomly, okay, distance L apart. Okay, so I have this, just showing that I have my historical presentation, okay, that is the Buffon needle problem that allow to approximate pi, okay, using, okay, needle and probability of intersection. And just to say that, okay, now I can drop these needles, okay, but from a computational point of view, okay, without needing to do the experiment in practice, can use my computer, okay, and do this very quickly, okay, this way, approximation of pi that are that accurate, okay. So if I want to translate what we have done previously in the language of modern probability. Okay, what can I say? We are going to consider a random variable z such that z equal to 1 if the randomly dropped needle crosses a line, okay, and 0 otherwise. So you have here a random variable that follows a Bernoulli distribution with a parameter p, that is the probability that z equal to 1, that is, in fact, in this case, the expectation, and that is my probability of intersection that I have computed to be this one. Okay? And now, what I have done, I have reproduced this experiment several times. That is, that I have dropped, okay, not one, but capital N needles. And what I have done, in fact, I have considered Z1, Z2, Zn, that is a capital N sample of capital Z, independent and identically distributed, okay? It's what I mean by an N sample. And what I have used previously is that, okay, what is Z1 plus Z2 plus Zn, okay? Z1 is equal to 1 if the first needle crosses a line, 0 otherwise. Z2, 1 if the second needle crosses a line, 0 otherwise. So if I do the sum Z1 plus Z2 plus Zn, I just recover what I have denoted previously by capital X, that is the number of needles that, okay, cross a line. Okay, so previously, I have said that capital X over N is an approximation of my probability of intersection. That is here just the expectation. Okay, so implicitly, the validity of the approximation, we have done previously was to say that in my situation here, when I have a capital N sample of capital Z, okay, this average approximates the expectation of Z. Okay, so we have just written in the language of modern probability, okay, the approximation that I have used previously. And the idea is to justify from a theoretical point of view the validity of this approximation. Okay, it's exactly what we are going to do now, okay, with two famous results that you have already studied in probability theory, okay. And the first one being the strong law of large number. Okay, so let me remind quickly what is the strong law of large number. Okay, so you have a probability space, where here set a sigma algebra and a probability. I denote by E the expectation and the P. And then, okay, the strong law of large number can be written this way. If I have a sequence of IID, so IID for independent and identically distributed random variables with, okay, for data in L1, okay, so here it means that this condition on the expectation means that X1 belongs to L1 of omega AP, meaning that the expectation exists, okay, in one sense, okay. Then if I denote by Sn the sum of them, you know that we have the fact that this mean, that is Sn over n, converges toward the expectation of X1 almost surely and in L1. Almost surely and in L1. Be careful, in this case, we don't have the convergence almost sure that implies the convergence in L1, and we don't have the convergence in L1 that implies the convergence almost sure, so I need, okay, these two, okay. You know that if you want to pass from almost sure to L1, you need domination condition. And if you want to pass from L1 to almost sure, but you have it, but only for a subsequence, okay? So we have both here. So if I have a sequence of IID random variables, okay, with a finite expectation, in fact, then the average of them, okay, converges toward the expectation of each of them. It's what we call the strong law of large number. So as an illustration here, I can show you this graph, okay? So what I suppose here, I suppose that x1 follows a Bernoulli of parameter 1/2. Okay, x1 follows a Bernoulli of parameter 1/2. So in some sense, we are in the case of the Buffon needle where the probability of intersection is equal to 1/2. Okay, and what happened here? But here I have plot. What I have plot? Okay, I have plot here in blue. You have Sn over n in blue. In red here, you have the expectation of x1. That is just, okay, 1/2 in my situation, in the case of the Bernoulli, okay? And then you see that when I increase, so here you have small n, the number of random variables I use in order to approximate my expectation, I see that, okay, graphically at the very least, okay, that the blue curve, okay, seems to converge toward the red one, the red line, okay, in this way. Just be careful, okay, another graph just to show you that this hypothesis is important if you want to have, okay, the strong law of large number. If I give you an example, okay, of a situation where it doesn't work, okay, so here I consider that x1 follows a Cauchy of parameter 1. What is the meaning of following a Cauchy of parameter 1? It just means that the density of x1 here is supposed to be something like that, 1 over 1 plus x squared. So maybe I need to have a pi here, something like this, okay? So it's the Cauchy distribution of parameter 1 here, okay? In order to obtain 1, in order to obtain the fact that here, okay, I can see very easily that I don't have an expectation here, because if you multiply this term by x, okay, you have something that is equivalent to 1 over x in plus and minus infinity, so something that doesn't converge, okay? And you see that here, if you apply, okay, so once again, here you have in blue Sn over n, and you have here the number of random variable you use in order to compute the average. But I see that I don't have the convergence, okay, of Sn over n. Sn over n doesn't converge, but in fact, okay, you can see that if you continue this graph, but you have something that is near from 0, and then, okay, you have something that happened like this. Then you increase, you will maybe seems to be not very far from 0, and then another, okay, change. So it was just a basic remark in order to say to you that if I want to apply the strong law of large number, okay, I need to have an expectation that is well defined for sure. Okay, and here it's just an illustration in the case where you don't have an expectation and you see that you don't have the convergence, okay, almost sure, of Sn over n. And what is nice with this strong law of large number, if I come back to the previous slide or this one, okay, is that here it's in the case of real random variables, but if you consider a sequence of random vectors, x1, xd here, okay, and if you denote this one by xn, it's the case where I have a random vector, so for d equal to 1, I am in this situation, okay, the strong law of large number will tell you that, okay, x1 plus xn over n converges toward the vector of the expectations, that is this one, okay, almost surely, and in L1, if the expectation, or if, let's write it this way, if x1 belongs to L1, okay? So what is nice with the strong law of large number is that, okay, you have it for real random variables, but you have it, okay, for random vectors. And the proof is very basic from R to RD because, okay, you can do the reasoning component by component, let's say, at the very least for the almost sure convergence. Okay, so it's just that you converge toward the vector of expectation, not to the expectation number. Yeah. So from a theoretical point of view, okay, this result that is in some sense a theoretical justification of the Monte Carlo methodology works for R or for R to the power D exactly the same. Okay. So I have this. So here I have given to you, okay, but why not? But I won't enter into details. You have here, so as you know, the strong law of large number is not a result that is easy to prove, okay? Not easy to prove, but we have some situations, okay, where it's not that complicated. In fact, if you increase a little the integrability condition on the random variables, then, okay, the proof is very short, and it's a good little exercise of probability. So it's exactly what I have written here. Okay, if I suppose that I have a fourth order moment, that is something that is more restrictive than to be in L1, then, okay, I can prove very basically, and have a look on this one if you are interested in, I can prove very basically that I have the convergence almost sure and in L1 of the average toward the expectation without complicated mathematics. Okay, so it's that easy to obtain it in the case where I am in L4 and not in L1. Okay, so I will just do a 5-minute break here. Okay, so let's continue. So what we have at this stage, so we have the strong law of large number that ensure the theoretical foundation of the approximation of an expectation by the average of n sample. Okay, and it tells us the convergence of this approximation, okay, when n goes to plus infinity, almost surely in L1. So keep in mind that I want to have an approximation, but I want also to have a control of the error I do. And as you know, probably, okay, in this case, the control of the error will be given by the central limit theorem, CLT, central limit theorem, okay? So I remind you the central limit theorem. And first of all, in order to remind you the central limit theorem, I can remind you what is the notion of convergence in distribution. Okay, so we say that a sequence xn converges toward capital X in distribution, and I will use this notation later on, if for all mapping from R into R that are continuous and bounded, okay, so CB means, okay, continuous plus bounded, then, so it means a parenthesis here, the expectation of f of xn converges toward the expectation of f of x when n goes to plus infinity. Here we have a sequence of real numbers, okay? So we have this, okay? And of course, if I have not a single random variable here sequence, but a sequence of random vectors, I have exactly the same definition if I replace the mappings continuous and bounded from R into R by the mappings that are continuous and bounded from R to the power D into R, okay? And what is nice is that, okay, if I have this convergence, okay, for continuous and bounded mappings, okay, naturally, this convergence extends, okay, to the case where f is an indicator function. Okay, so we know that an indicator function a priori is not continuous. Okay, so let's take, for example, the indicator function of an interval, the one that I will use later on. Okay, if you take something like this, okay, you have 2 points of discontinuities at a and minus a, but okay, using approximations of this indicator function by continuous and bounded mappings, okay, then it can be proved that if I have this convergence for any mappings continuous and bounded, I will have it for all the mappings of this form, okay, that are indicator functions, okay? So this is the convergence in distribution, okay? And the interest of this convergence in distribution is that, okay, but it is implied by all the other way to converge, okay, you have in mind. So for example, the convergence in probability implies the convergence in distribution. Convergence almost sure implies the convergence in distribution. The convergence in L2 implies the convergence in distribution, and so on, okay? So all the other way to converge, okay, will imply the convergence in distribution. That is the weakest way if you want to converge, okay, for random variables. So what is the central limit theorem, okay? So I have it this way. Let's write it this way. Okay, when I have a sequence of IID random variable, okay, I suppose them to be R, but I can extend this result to the case where I have a sequence of random vectors, not a sequence of real value random variable. Then if I suppose them to be in L2, so here the hypothesis is a little bit stronger than the one in the strong law of large number. I need them to be in L2. That is, the variance exists, if you want, okay, and so the expectation exists. Then this quantity converges in distribution toward a n01, okay, where sigma square is the variance of x1 that exists, and here I have the expectation of x1 that also exists because I have this integrability condition here. So if I consider this quantity of interest here, what is it? It is Sn minus n expectation of x1 over the square root of n sigma. I can write this quantity this way. I can write it as Sn over n minus the expectation of x1. In fact, what I do, I put n into factor here, and if I do this, I will obtain here square root of n over sigma. And I know from the central limit theorem that this quantity converges in distribution toward n01, okay? Where sigma is in fact the standard deviation of x1, okay? So sigma is the square root of the variance of x1. Okay, so what is the intuitive meaning, the classical intuitive meaning of the central limit theorem? But just the fact that from the strong law of large number, so the strong law of large number, that this one converges almost surely and in L1 towards 0. Okay, so I have something here that converges towards 0 in this sense. Here I have, of course, something that converges toward plus infinity. So I have a form that is undetermined, okay, in the classical sense. But if I multiply this quantity, in fact, okay, I have the convergence of this product towards something. So be careful, the convergence holds, but in distribution, not in the almost sure sense and not in the L1 sense, but in the sense of the convergence of distribution, okay? And it means in some sense that, okay, this one converges towards 0, this one converges toward plus infinity. If I multiply them, okay, I obtain a convergence in the sense of the convergence of distribution. So it means that intuitively, the speed of convergence of this one toward 0 is more or less a constant multiplied by 1 over the square root of n. Okay, because this one converges toward plus infinity at the speed of square root of n. If I want that the product is convergent, this one has to converge towards 0 at the speed of 1 over the square root of n up to a constant. Okay, so in some sense, you have a precision of the speed of convergence in the strong law of large number. This is the way we can intuitively interpret the central limit theorem. Okay, and as you know, the interest of the central limit theorem will be to be able to build confidence interval, asymptotic confidence interval. So just to illustrate what I have said here, you have here what I have plotted here. I have considered uniform on the interval 0, 1, random variable. I have considered an n sample of size 500 of such uniform on the interval 0, 1. And what I have plotted here, I have plotted the realizations of this quantity here, building the associated histogram, of such quantities computed for uniform on the interval 0, 1 and 500th realization. And then I see that in this case, you have here, it's the density of N01. Here you have the empirical density of square root of n over sigma Sn minus the expectation Sn over n minus the expectation of x1, and I see that they coincide in a good way. Okay, and what is nice with the central limit theorem is that I have an easy extension of the theorem, in the case where I have random vectors, So the only thing I have to impose in the case is that here you see that you have the inverse of the standard deviation, So you have a matrix that you need to be able to invert, So the variance covariance matrix has to be bijective, if I want to be able to extend these results, to the higher dimensional case, But I have exactly the same thing. And what is nice is that, if I replace sigma by, so let's write it this way. If I change R into R to the power D, but I will replace sigma minus 1 by capital sigma minus 1, where, sigma square, capital sigma square is the variance covariance matrix, And what is nice is that I don't change the square root of n when I pass to the real valued case to the vectorial one. That is, the speed of convergence in the theorem doesn't depend on the dimension of my problem. Doesn't depend on the dimension of my problem because I have always the square root of n here that is independent on the size of the random vectors I consider in the central limit theorem. So I have this. And as you know, a nice feature of the central limit theorem is that, I am able to build asymptotic confidence interval in this situation, So what I know that, square root of n over sigma Sn over n minus the expectation of x1 converges in distribution toward n01. Okay, so it means that the expectation of f of square root of n over sigma Sn over n minus the expectation of x1, okay, converges toward the expectation of f, let's write it this way, of n01. Okay? When f is continuous and bounded. But I have said to you that in the convergence in distribution, I can also take for f indicator function. So I will take an indicator function of this form. Okay, the indicator function of the centroid interval minus AA. And if I do this, okay, what I obtain, so I will have expectation of indicator function that will be, in fact, probability. I will obtain from this one that the probability that the square root of n over sigma Sn over n minus the expectation of x1 greater than minus a less than small a converges toward the expectation of, okay, indicator function between minus a of n01 this one can be written as the probability that minus a sigma over square root of n is less than Sn over n minus the expectation of x1 less than a sigma over the square root of n converges toward, okay, this one that is just the integral between minus a and a of what? Of the density of n01 dx. Okay. And what is nice, okay, is that classically we know from tables that if I want to make this term to be big, and for example, in general, we take 95%, okay, this one is equal to 95% if A is equal to 1.96. And so in this situation, I have for large n, this probability that is near 95%. And so I can build this way, this confidence interval, okay, with a confidence of 95%. That is, I just have to handle a little this expression to obtain that the expectation of x1, that is the quantity that I want to approximate, belongs to this interval for large n with a probability of 95%. And what is nice here is that you have a size of this confidence interval that is equal to this quantity. Okay, 2 times 1.96 sigma over the square root of n. Okay, and it represents here the magnitude of the error I do. I belong to an interval, a random interval that is centered at my approximation, that is Sn over n, and with a length for this interval that is 2 times 1.96 sigma over the square root of n. And of course, what I remark is that when n becomes bigger and bigger, the size of the confidence interval will go to 0, because this term here goes to 0 when n goes to plus infinity. And I also remark that the size of sigma is fundamental in order to control the size of my confidence interval. For a fixed n, okay, the length will be drive by the size of the standard deviation. Okay, so it means that if you have a very, very big sigma at the beginning, in order to obtain reasonable size for confidence interval, I will have to take very big n. Okay, so something that will take time to generate. Okay, so this is something that you probably already know. Okay, the way to build asymptotic intervals from the central limit theorem in order to have, okay, a control of the error I do when I approximate this expectation by this number here in the sense of asymptotic confidence interval. Okay, here I have just reported the table of the distribution function of the N01, okay, in order to show you that it's the table I use in order to obtain what I want. That is, okay, so if I take my previous example, I am interested what I want to find. I want to find A such that the probability that the absolute value of my N01 is less than A. I want it to be equal to 95%, okay, for example. So let's use this table in order to find such a A here. What is this? It's the probability that my N01 is less than A, greater than minus A. I can write it as the probability that my N01 is less than A minus the probability that my N01 is less than minus A. Okay, so I have this one. What is this one? By symmetry of the density of N01, I obtain here the probability that my N01 is less than A minus the probability that my N01 is greater than A by symmetry of the density of N01. And so I obtain what? This one is equal to 1 minus the probability to be less. So I obtain here 2 times the probability that my N01 is less than A minus 1. And so in order to solve this equation here, I have simply to solve probability that my N01 is less than A is equal to 1.95 divided by 2. That is equal to 0.975. And if I use this table, so to solve this is just to find the A such that the distribution function of my N01 is equal to this number. Okay. And I see in this table that you have here the number of interest. Okay, that is this one here. That you will obtain for A. That is given by what? By 1.9 here plus 0.06. And that's why we find here the A that is 1.96, the one that I have used in the previous slide here. It's the one I obtain here from the table. And of course, you can increase the precision. You can take here 0.99, okay? And if you do this, okay, you obtain another A related to a confidence interval at a level of 99%. But in general, in practice, okay, 95%, okay, is the level we use and the level that we will use in this course. Okay, just a little remark concerning what we have done. So what I have said here, that from the strong law of large number, I can approximate an expectation theoretically by an average of independent realization if they are in L1, okay? with a convergence almost sure and in L1 that is ensured by the strong law of large number. And that, okay, in order to control the error I do, I can use confidence intervals taken at a certain level, okay? So I have this. But I have a problem if I do this. I have a problem if I want to use this methodology in practice, because keep in mind, okay, what I want to do. If I want to control my error here, I need to know this confidence interval. In particular, to have in practice this confidence interval, I need to know sigma. But what is sigma? Sigma is the standard deviation of x1. So we are in a situation where I want to approximate the expectation. I can do it from the strong law of large number, but in order to approximate it, okay, and to have a control on the error I do, I need to know the standard deviation. But unfortunately, in general, if you don't know the expectation of a random variable, and if you are not able to compute it explicitly, you are not able to compute the standard deviation, because in the expression of the standard deviation, you need to know the expectation of the random variable. Okay, so here you have a theoretical control of the error given by the central limit theorem, but if you are not able to compute sigma or to approximate sigma, okay, it's not something that you can use in practice. That's why, okay, in general, we are going to replace in practice sigma, that is something that I don't know a priori here, by an estimator of sigma. And this estimator is well known, okay? It's what we call the empirical variance, okay, of the n sample. So let's write it this way, and I will explain to you what happened. So we have seen together that the expectation of x1 may be approximated by 1 over n sum from k equal to 1 to n of xk, with a convergence that almost surely n in L1. So suppose that, okay, you are interested in sigma square. That is the variance of x1. What is it? It is the expectation of x1 minus the expectation of x1 square. Okay? So something that I can also write as expectation of x1 square minus the expectation of x1 square. Using this kind of approximation, okay, I said that I can approximate this quantity by the 1 over n, the sum from k equal to 1 to n of xk square minus the square of the expectation, that is minus the square of my previous approximation. And you have here an estimator that is called the sample variance. And I will denote it by, let's say, sigma n square. Of course, if I use the strong law of large number, by the strong law of large number, this one converges toward the expectation of x1 square, and this one, okay, because I have the convergence almost sure of this one, and you know that the convergence almost sure is stable if I apply a continuous mapping here, the square mapping. So here I converge toward expectation of x1 square. I converge almost surely by the strong law of large number. So it means that this one converges at the end almost surely toward what I want, that is sigma square. Okay? Okay. I have the convergence of my estimator toward what I want to estimate, okay, when n is large, okay? My estimator is said to be, okay, efficient. But unfortunately, if I compute the expectation of sigma n square, I obtain the following. I obtain n minus 1 over n sigma square, meaning that my estimator sigma n square is a biased one. Okay, is a biased one. It means that in expectation, it's not equal to what I want. It's not very far because when n is large, okay, this quantity is near from 1, but it is not equal to sigma square. I have a little difference between them that I call the bias. Okay, and so that's why we defined a new estimator in order to remove this bias. A new estimator that is equal to n over n minus 1 sigma n square, we call the corrected sample variance. And why we do this? Because according to what I have said, this one converges almost surely towards sigma square. This term converges almost surely toward 1. So this one will also converge towards sigma square. And what is nice is that when I take the expectation by construction, its expectation is equal to sigma square because I have this equality here. Okay? And we have these two properties. So you have here the corrected sample variance, that is an estimator that converges almost surely towards sigma square, and that is unbiased. And in general, in practice, it's the estimator that you will use if you want to approximate, okay, the variance of a sample, the variance of a sample. Okay, so at this stage, what I have from the strong law of large number, I have a theoretical methodology in order to approximate an expectation using average of samples. By the central limit theorem, I can build confidence interval, but unfortunately, these intervals depend on sigma that I don't know a priori. And here you have a way to approximate sigma or sigma square, and so sigma. And in fact, I have this result that will solve my problem. That is, okay, if you have IID random variable, in fact, the central limit theorem holds even if you substitute sigma n at to sigma. In the central limit, the classical central limit theorem, you have sigma here. Here I replace sigma by the square root of the corrected sample variance. We have proved in the previous slide that sigma n hat, okay, is okay something that is so sigma n square is an unbiased estimator of sigma that is convergent. Okay, and we can prove that we have the convergence of this quantity toward the n01s, okay, as the one we have if we have sigma instead of sigma n hat here. Okay, and what is the trick that allows to have this one is what we call, okay, it's a so-called lemma in probability. It's what we call the Slutsky lemma that tell you that if you have a sequence that converge in distribution, another one that converge in distribution toward a constant, then the product converge in distribution toward the product with a strong assumption that is this one. Okay, it's not that the convergence in distribution is stable by product. No, the convergence in distribution is stable by product if one of the convergence is toward a constant. And here it's exactly what we have, because here, okay, I can write my quantity of interest I can write it this way. Sigma square, and so if I do this, I have here sigma square over, not sigma square, excuse me, sigma over sigma n hat. And what I know, by the classical central limit theorem tell me that this one converge in distribution toward n01. And here I have the convergence almost sure, and so in distribution toward 1. Okay, if I apply the Slutsky lemma, here I have something that converges in distribution toward a constant. This one converges toward n01, and so the product will converge toward the product that is n01. Okay, so I have a version of the central limit theorem that allow me to extend the central limit theorem in the case where I don't know the variance of my sample, substituting the corrected sample variance to the variance. And so now the construction of confidence interval can be done classically. I use this result, and okay, it means that my confidence interval will take the form of something like this, that is Sn over n minus 1.96 if I want a confidence interval at a level of 95%. Here you have sigma n hat over the square root of n, Sn over n, plus this one, with a size for the confidence interval that is, okay, that is 3.92 sigma n hat over the square root of n. So I can do exactly what I have done in the case of the classical interval here, but I just have to substitute sigma n hat to sigma in order to have a confidence interval here, a confidence interval that I am able to compute explicitly if I have my n sample at the beginning. Okay, so I have it. And here now you have a complete way, okay, to approximate an expectation and to have a control of the error in the sense of confidence interval. Okay, so conclusion of this first part here, okay? Conclusion of this first part. So if I want to compute the expectation of a function of x, okay? So it's my random variable here. By Monte Carlo methods, what I have to do? I have to first generate an n sample of the distribution of x, okay? It means that, okay, I need to generate x1, xn that are iid with the xi that follow, so that are equal in distribution. To d, okay? And then in order to approximate the expectation of f of x, I can compute the average of the related sample, okay? And I know that from the central limit theorem, or excuse me, from the strong law of large number, we tell you that this approximation will converge almost surely and in L1, okay, toward the expectation of f of x. And the only condition that I need to impose in order to have this is that f of x belongs to L1. Okay? And what is nice here is that, okay, you have an integrability condition on f. The condition is fx belongs to L1. You have no regularity condition. Conditions on f. only integrability condition, something that is really weaker, no regularity condition on F. I don't mind about the fact that F is continuous, F is C1 or something like this. I just need to have, okay, this integrability condition. Okay. And once I have used the strong law of large number in order to approximate, fulfilling this hypothesis, then I precise the confidence interval that will be for me a control of the error at a precise level. Okay, so it means that it's very easy to do here in practice. So, and from a practical point of view, it's the only point that we have not discussed about, okay, today. But I will say a few words, okay, in a few minutes concerning these points, or maybe in the next session, I don't know, I will see, okay. That is how to generate in practice, okay, an ensemble from a particular distribution, because it's something that is mandatory in order to be able to then implement this one. And once you have done this job here, it's very easy to implement from a computational point of view, because what you have to do, you have to compute this one. So you have to do a little loop in order to do this. And then you have to compute the confidence interval where you have to compute the corrected sample variance. And it's once again average. So you can do it, okay, by basic loops, okay? So from a computational point of view, to implement the second and the third point is very, very simple. So advantage, no regularity condition on F, and advantage, precise. So having a control of the error through the notion of asymptotic confidence interval given by the central limit theorem. And I have said to you that in the central limit theorem, the size of the error I do is of the form a constant over the square root of n, okay? And it's something that is independent on the dimension of my problem. It means that here, if I take x that is a random variable or x that is a random vector, I have exactly the same way to control the error I do with the same speed of convergence in the central limit theorem. So it is one of the two main advantages, okay, of this methodology. It's what I have summarized in these slides. Okay, so very easy to implement. No regularity on F, only integrability conditions, and the control of the error through the notion of asymptotic confidence interval is something that is independent of the dimension of my problem. Okay, and in fact, if you see this, it's something that is completely the contrary of what we have done at the very beginning of this session. When I have reminded to you how to approximate an integral by Riemann sum, I need regularity in order to obtain the convergence. I need regularity to obtain the control of the error, to be C1 at the very least, okay, to have a good control of the error I do using Taylor expansion. And then I have said to you that if I am not in the univariate case, but in the multidimensional case, okay, but the error I do will be controlled by a term that will be weaker and weaker, okay, if I increase my dimension. Something that I don't have for the framework of Monte Carlo methodology. But of course, I have a price to pay for these advantages. And the big price I have to pay is the fact that the error I do is a random variable. Okay, the very beginning of the course, I have proved that in the case of the Riemann sum theorem, if I impose regularity on small f, I have something of this form. And here you have a bound, a deterministic bound. Okay, so it means that whatever happens, you are sure that this inequality is fulfilled. In the case of the central limit theorem, the expectation belongs to a confidence interval here. With a probability, so that may be big, 95 or 99 as you want, okay, but it's only a proba that you have. If you are unlucky, you may be outside the confidence interval. So the very big price to pay when we use Monte Carlo method is the fact that, of course, since we use probabilistic tools, we leave, okay, the world of deterministic tools to enter the world of random one. And so all the notion we are going to handle will be random notions. In particular, the error we are going to deal with will be an error that is in the sense of a random error, a random variable that I am able to control, okay, but that I am not able to know very perfectly. And the last point I want to emphasize today, okay, concerning Monte Carlo methods is that, okay, so if you see what I have said today, you can say, okay, in fact, Monte Carlo methods are very easy to do because, okay, it's what? Central limit theorem and strong law of large number. The only point that I can focus on is what I have said previously, the fact that I need to answer this question, how to generate practically samples of random variable. But up to this technical issue here, then I have to do loops and I have to compute confidence interval. But it's not that simple because in fact, okay, a course on Monte Carlo methods, okay, will start in fact now. A course on Monte Carlo methods is just not to say that, okay, we use the central limit theorem and the strong law of large number, and you have a random way to approximate an expectation and to control the error in the sense of asymptotic intervals, okay, of confidence. No, because if you just naively apply Monte Carlo methods this way, but in general, they are very bad. Okay, so in fact, what will be a course on Monte Carlo methods? A course on Monte Carlo methods will be a course where I will learn you how to generate samples of random variables and how to handle, okay, the use of the central limit theorem and the strong law of large number in order to obtain methodology that it is possible to use in practice. Because if you do naively Monte Carlo methods, in general, they are very, very slow. And I will show you this on a little example. You are going to understand that if I use directly a Monte Carlo method, even in a very, very basic situation, I can be in the situation where, okay, I can say anything, in fact, concerning my approximation and the error I do. Okay, so I repeat that the objective of this course is not to be a self-contained presentation of Monte Carlo methodology, but I repeat that on my website, I have, as I have said at the beginning of this session, if you want to enter into more details of Monte Carlo methods, you have supplementary material in my website, okay, where you are able to do this. So to conclude the today's session, okay, let's see what happened in a very basic example. The very basic example is this one, okay? So suppose that I am a student, okay, that doesn't know perfectly my course of probability. In particular, I don't know that if I want to compute this expectation, okay, this expectation that is just the moment generating function of a Gaussian random variable at the point beta, I can do it. I can do it because in my course of probability, I know the characteristic function of n01, and in fact, the characteristic function of nm sigma square. And I also know, as a byproduct, okay, the moment generating function. So I know from my course of probability that this quantity, as I have written here, is simply equal to exponential beta square over 2. Okay, but suppose that I don't remind this. That is, okay, I have this expectation to compute. I have forgotten that it is related to the characteristic function of n01. And so I try to use what I have learned today in order to approximate this expectation by using Monte Carlo methods. Okay. What I have to do, as I have said previously, since it's a function of n01, a Gaussian distribution with mean 0 and variance 1, if I want to use Monte Carlo methodology, what I have to do, I have to generate an n sample of n01. For the moment I don't know how to do it, I will see this next session quickly, okay? But suppose at this stage that I am able to generate an independent realization of n01. And I know from the strong law of large number that if I want to approximate this expectation using this n sample, I just have to compute this average here that I will denote by in, okay? And when n is large, okay, I know that this quantity converges almost surely n in L1 toward the expectation of interest. So the error I do, okay, doing this is controlled by, I have said, the size of the confidence interval, okay? And I know that the size of the confidence interval is given. So I will consider the error I do here, approximation minus the quantity of interest. I will approximate it using, okay, the size of the confidence interval. And we have seen that the size of this confidence interval is given by this quantity in green here. 2 times 1.96 multiplied by sigma divided by the square root of n, okay? And here, I won't be interested in just the error I do, but in the relative error, that is the error over the true value. So error over the true value, and so I obtain this quantity over the true value, that is over I. Of course, I am able to compute this quantity. I am able to compute this quantity explicitly if I am a good student. That is, if I am able to compute this one in relation with the characteristic function of n01, I will also be able to compute sigma, and sigma is just the standard deviation of this one. Very easy to compute because, okay, I have here sigma square, that is what? Is just the expectation of this one square that is exponential to beta n01 minus the expectation of exponential beta n01 square. This one may be computed using the moment generating function of n01. This one may be computing using the moment generating function of n01. If I plug in this expression all the things that I am able to compute, I obtain this quantity in red here. That is, okay, the relative error I can deduce for the approximation of I by in, okay, using, okay, confidence, asymptotic confidence interval, okay, as benchmark, okay. I have this. And now we are going to see what happened in this situation. Okay, so you agree with me that I have a very basic expectation to compute. In fact, one that I am able to compute explicitly if I know my course of probability. But if I use Monte Carlo methodology in order to approximate, I have this relative error. Okay, so what happened in practice for this relative error? Okay, I obtain the following. If I take beta equal to 1, it's very easy to see that in order to obtain a relative error of 10%, okay, that is a reasonable one, okay, not a very good one, but something that is reasonable, I need to take n greater than 1,000. Okay, so why not? It's something that is not that terrible to do from a computational point of view. Okay, if I take n greater than 1,000, I am sure to obtain, okay, in the sense of the central limit theorem, okay, a relative error that is less than 10%. Okay, I have this. What is interesting now, okay, is what happens if I take just a beta that is a little bit bigger. If I take beta equal to 5, okay, I am in the situation where in order to obtain a relative error that is less than 100%, so that is something that is completely ugly, okay, I need to take n greater than 7 times 10 to the power 10. So it means that in the very basic case where I have to compute my expectation I for beta equal to 5, and knowing that my beta, my value is just the exponential of 25 over 2, exponential of 12.5, something that is very easy to compute and approximate. Okay, so if I use Monte Carlo methods, I am in the situation where, okay, it's in fact numerically impossible for me to obtain a relative error that is less than 100%. And in particular, I have shown you that for beta equal to 5, I can approximate my exact value this way, computing the exponential. And if I use here 100,000 element in my sample, I obtain an approximated value that is this one, where a confidence interval at the 95% level, that is this one. So you see that the confidence interval you obtain here is completely different when the value that you need to approximate. So if you apply naively Monte Carlo methods in this situation here, okay, so you will do it for n equal to 100,000, so something that is that big, in fact, okay, but the confidence interval that you will obtain will be very, very far from the value that you want to approximate. So it means that in practice, okay, you have something that it's not possible to use. Okay, you have a precision that is completely bad in this situation. And where is it coming from? Okay, of course, it comes from the example I have taken, in the sense that here, okay, the sigma, that is this quantity that I am able to compute explicitly, this quantity, in fact, becomes very big because it is related to an exponential. So if I increase a little bit my beta, since I have an exponential, okay, I will have an explosion of sigma, okay, that won't allow me to be able to use Monte Carlo method in order to approximate, okay, I repeat, approximate something that I am able to compute very easily, okay. So I have a sigma that is too big, okay, and so, okay, even if in this very basic situation, it's not possible for me to use Monte Carlo methods. Okay, so I repeat that I won't do in this course a complete course on Monte Carlo methods, okay. I will just show you next session, okay, how I can use them in practice to price and to hedge in the Black-Scholes model. And we'll see what will be the numerical issues concerning these two objectives, okay, in particular, in order to hedge, that is in the computation of the quiz, okay. But I repeat that if you want to have more details concerning, okay, this little introduction concerning Monte Carlo methods, okay, but then you can have a look on my website. Where is it? You can have a look on my website, and here you will find, okay, 5 courses concerning the way to implement in practice, okay, Monte Carlo methods in finance, in particular in relation with how to generate samples of random variables, okay, and how to overcome the problem I have underlined with the computation of the expectation of exponential beta of n01, okay, that is how to overcome this problem, okay. I won't have the time in this course to enter into all the details of this, okay. Next session, I will focus on the Black-Scholes model in order to show you that I have some problem in this situation and some problem that I will be able to solve using, okay, Malliavin calculus. Okay, so see you next week, okay, in order to continue this course. Bye-bye.